This is the second part of section 6.2. We're going to talk about orthogonal decomposition and orthogonal projections. So we have a theorem that tells us any orthogonal set of non-zero vectors is linearly independent. And we have another theorem that tells us if we have a set of orthogonal vectors and they form a basis for a subspace W, then every vector in W can be written as this. All right. Now the proofs of these theorems are at the end and they're not difficult, but since we're doing this in a video, I'm not going to include the proofs here. The corollary is that if you have an orthonormal basis, then this formula, I'll say formulas 1 and formula 2. Formula 2 comes from formula 1 with each denominator equal to 1. Because if the lengths of the vectors are 1, then the dot product of the vector with itself is 1, and so those denominators just disappear. So formula 2 is a special case of formula 1. You do need to memorize this, and it's really not that bad. Typically we'll only have 1 or 2 vectors. It won't be ... up to up. For example, in this example here, we've got 3 vectors, u1, u2, u3, and those vectors form an orthogonal basis of R3, and we want to write y as a linear combination of those vectors. So each time you use a formula, you want to write it down, which I did. And let's just compute these quantities. Y dot u1. So y dot u1 is 3, take away 7. That's negative 4. u1 dot u1 is 2. So we have negative 4 over 2 u1. And then we're going to add on y dot u2. So y dot u2 is 10. Divide by u2 dot u2, which is 2. u2. And then finally add on y dot u3, which is 4. Divide by u3 dot u3, which is 1, u3. So that's negative 2 u1 plus 5 u2 plus 4 u3. We've written y as a linear combination of 3 other vectors. Now in the old days, the way you would have done this is to reduce the augmented matrix u1, whoops, I don't want commas there. I just want u1, u2, u3. You put those in as columns, and then you augment with y. And when you reduce that, you get the weights, and the weights would have come out to be negative 2, 5, and 4. And you can still do that, but this gives a much simpler way to get the answer. But it is dependent on the fact that you have to have orthogonal vectors to start with. If you don't, then you have to do it the old-fashioned way by reducing. All right, why don't you guys pause the video and try this one yourself? Okay, hopefully you did that. First, we want to write down what the formula we're going to use. Y is y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 u2. Now I stated in the statement of the problem, I stated these were orthogonal vectors, but let's just do a quick check. u1 dot u2 is 12 minus 12, which is 0, check. All right, so now let's compute these dots. Y dot u1 is negative 4 plus 30 would be 26. And u1 dot u1 is 9 plus 4 is 13. And then y dot u2 is negative 12 minus 40, that's negative 52, over u2 dot u2, which is 52, u2, So that's 2u1 minus u2. And when you do your next test, I'm going to want to see this work. I'm definitely going to want to see that you write out the formula that you use, whether it be this orthogonal decomposition theorem or the formulas in the next box on the next page. Okay, so orthogonal decomposition and projections. So here's an example. If y is negative 3, 4, which I have graphed in red in that picture, then we can write y as the sum of a vector in the direction of u, which is negative 2, 1, and a vector perpendicular to u. So y can be written as y hat plus z. Let's just check, is that really y when we add together? We get negative 3, 4, which is y. So yes, y is y. And then, is y hat parallel to u? Well, y hat is 2 times negative 2, 1, which is 2u. So that means y hat is parallel to u because it's a multiple of u. And so you can see in my picture there, I've got u, and then y hat is just a little bit longer than u. Actually, it's twice as long as u, but it's parallel to u. And then z is over here. Z is 1, 2, and I claim that y hat and z are perpendicular, and so the check for that would be z dot y hat. That's 1, 2 dot y hat is negative 4, 2. So yes, that is 0. So that's called an orthogonal projection. When we project y onto the line spanned by u, we call that an orthogonal projection, and then we call this decomposition here an orthogonal decomposition. So the exact statement is in the next box. So you definitely have to know this stuff. If u is a vector in Rn, and L is the line spanned by u, then the orthogonal projection of y onto L, we typically call it y hat, and the notation is proj, you write P-R-O-G, so P-R-O-J, sorry, proj onto L of y, or since L is spanned by a single vector u, sometimes people will write that as just proj onto u of y, and it's y dot u over u dot u times u. All right, and we can write y as y hat plus z, where z is just the difference between y and y hat, and that's called the orthogonal decomposition. So two big formulas here: the projection of y onto u, and this decomposition as y equal y hat plus z. Now z, if we look at this picture here, if we project y onto L, that's this vector here, that's y hat. Z is perpendicular to y hat. Z measures the distance from y to L. And so that's the length of z, which is the length of y minus y hat. So let's try doing these three things with an example. So we've got y here, u, and L will be the span of u. So find y hat. All right, if we're going to use a formula, we should write it down. Y hat is y dot u over u dot u, u. And if you write it down every time you use it in your homework, you're going to have a much easier time remembering it. So y dot u is negative 24 plus 4 is negative 20. U dot u is 10, and that's u, so that's negative 2, and I'll put in u is 3, 1. That's negative 6, negative 2. And in this chapter a lot, we're going to write our vectors in linear format. So you write -6 comma -2. So either one is fine. All right, now write y as the sum of two vectors, one parallel to u. We already did that. The one parallel to u is y hat, and one orthogonal to u. That will be z. So z is going to be y minus y hat. Y is -8 comma 4. Now I want to subtract y hat, -6, -2. So that's -2 and then 6. And then we found the two pieces, but we have to do what we're instructed to do, which is to write y as the sum of two vectors. So y is equal to y hat, which is -6, -2, plus z, which is -2, 6. So this is y hat, and that's z. Now, there's a safety check you can do. Check. All right, so 1, is y really y hat plus z? Add these two vectors together and see if you get y, which was -8, 4. So when we add those two vectors, we get -8, -2 plus 6 is 4, yes. All right, and then the second safety check is that y hat and z are supposed to be perpendicular. They're orthogonal vectors. So we want to check, is y hat dot z 0? And so we go over here, we get 12, minus 12 is 0, check. Orthogonal decomposition is unique, and so we've done it correctly, because if those two things are satisfied, that's the orthogonal decomposition. All right, and so I have a picture here of what's going on. Here's y in red. U is the line spanned by 3, 1. So here's u, and the line spanned by u is dotted there. Y hat is -2, 6. So this is my y hat, and it is indeed parallel to u. It's just pointing in the opposite direction. So this is y hat. And then z is -2, 6. So this would be z. And if you translate z over here, you can see that the length of z gives the distance between y and y hat. So that would be the distance from y to the line L. And so this last part, we want the length of z, which is square root of 4 plus 36, which is the square root of 40. Okay, and I'm going to do the last part in another video. Talk about orthogonal matrices, and there are some practice problems that you should probably do before you watch that last video of this section, because you can do part A and B right now.